guess we'll kick it all off. So this is industrial strength testing for complex software. Hopefully it should be fairly clear from the slide, and hopefully you're all in the right talk. If not, we're going to lock the doors and make sure you hear about some testing. So over the course of one's career, I think it's fairly natural at various stages to find yourself particularly interested in a topic or an area and wanting to explore it more deeply. For me, that has become testing. In particular, ways of thinking about testing that impact the ways that we test the software that we write to do it more effectively. So just a little about me. My name is Ash. I'm an engineer at Datalust. We're a Brisbane-based company. I maintain some open source packages in the Rust ecosystem. I've been a software professional for about 15 years now. In the last 9 of those, I've spent working on the same product, which is a fairly unique length of time to spend in the same code base when oftentimes you may find yourself on short-term engagements moving along things. And so I think that's given me some interesting insight into the long-term life cycle of software and the impact that testing has across such long time frames. So today we're going to be looking at some general approaches to testing and ways of thinking about testing through a safety-oriented lens. So using methodologies that are used in more safety-critical industries and then sort of like diluting them down to the needs of our software systems and how they can still help us there. We're going to look at a few different testing techniques that we use and that we've developed for testing our own software system and how those might be interesting in the systems that you build. So I'm not going to be talking about specific methodologies too much. I'm not going to be trying to convince you that you need to learn and adopt TDD or any other kind of methodology like that. I'm also not going to be telling you how you can offload all of this work to agents and have them do it all for you. I think that the expert with AI angles tends to like flatten everything to a single dimension. But what we're going to talk about today can be mapped onto whatever tools and processes that you use, whatever way that agents may be involved in that. So we'll start with a little bit of context. So the software that we build is called Seek. It's an application diagnostic server. So you send your open telemetry, logs and traces and metrics to that. It then stores those for you and then surfaces them back up so that you can review them and see what's going on. Seek has been in production since about 2013, so 13 odd years now. It's primarily a JavaScript or TypeScript user interface talking to an ASP.NET Core app server and then with a big Rust database engine behind it that we build. And very recently, the size of our Rust code base just overtook the size of our C# one. So we are now primarily a Rust dev shop and not a C# one. So let me give you a bit of an example of how Seek works, just so that we can kind of frame our discussion on our testing a bit. So this is Seek. It's accepting some events at the moment. Usually what you will do when you open up Seek is that you will try and find something, usually some sort of an error that has occurred. So we can filter on those and we can have a look at some errors. Seek has a fully fleshed out query language. So it is basically a database. So in addition to just finding stuff using little filters like this, I can also say find all of the events where the level is an error and then group by, what was it, request path or something, I think? Group NI, thank you. And so we can run that and we can get like a regular query result that looks like something you get out of a normal SQL database. So if I was to explain that, for instance, what we're looking at here is a plan of the query that we're going to run. So something like you would also see in SQL Server. So at the bottom here, we are from the underlying data source projecting out some columns. We are going to run a condition on those. We are then going to run a grouping over one of those columns, and the aggregation is just a count of true because we just want the number of things. We are then going to have an asynchronous channel between that layer of our query and the layer above it, which is then going to take those results from possibly multiple instances of what's running below, and then it will merge those together by rerunning the grouping and then summing up the counts from all of the individuals and to give us the final result. So basically everything that goes on from the bytes on disk all the way up to the result that you see in the UI is our domain of stuff that we build. So to give you another view of that, we start with some query text. We then have a parser that parses an AST from it. We then hand that AST to a planner who gives us an initial plan. It looks very much like the one we just saw, but it's a lot simpler. We then have an optimizer that takes that initial plan and produces one closer to the one that we saw there, where it may parallelize bits and shift operations around to try and make the query that we want to execute more efficient. We then take that plan, which is like a sort of an abstract layered notion of things that we need to do to satisfy the query, and we then materialize it into a set of vertexes in a data flow where each vertex maps to some concrete portion of the underlying data source, runs some computation over that, and then has a channel to another vertex that will then receive those results and process them. From that materialized plan, we then hand it to a distributor who will produce an executable job of that, so where the vertexes then become functions that we can run. Though that job then goes onto the job pile, which is not quite a queue and it's not quite a set, so it's a pile. And then we have the local thread pool or remote nodes who will pull off that pile, execute the work, and then pass the results back on to the end user. So even in here, there is a fairly complex set of components that all interact in order to satisfy the execution of a query. But if we were to take, say, a less horizontal look and pick any of those and look vertically, there's also a lot of complexity hiding behind each of those. So if we look at the concept of a job, for instance, a job is made up of job vertexes, where the vertexes are mapping to some underlying data source, which in our case is like this stream, which is a row store, or the series, which is a column store. Within the stream, we have all of these concerns around JSON and compression, and in the column store, we have a whole lot of specialized machinery for working with columnar data as well. And then underneath all of those, there is an underlying byte store, which gives us our ACID semantics in the actual on-disk file formats. So there are a lot of moving parts in our software stack. So a lot of how we work is also informed by the shape of our team itself. It's not just what we build, but it is who we are and how we build it. So we are a very small team of engineers. There's 4 of us total, 3 of us in engineering. We are also the support team. We are also the sales team. So we wear a lot of different hats. And that comes with some challenges. The biggest of those is that we have really limited bandwidth to do anything. We tend to move around as one unit, and once we've visited an area and then we've moved on, it may be years before we actually can come back to that and do any more work on it. So we need to leave things in a state where they will stay stable for years without us interacting directly with them. Seek itself is self-hosted. So once we ship a binary, we have no control over the operating environment besides some nudging through documentation that nobody reads. So we only see half of the process of running Seek. We also have many active versions in servers, so we can't take a look at, say, our issue list or our support queue at any one time and draw conclusions about the state of the current code base that we have, because there are so many different versions that people are running, so many different environments that they're running it in. So it's really hard to do really quantitative analysis on the code base itself based on what we observe in the field. So that leads to some approaches. The first is that we have a very early, heavy focus on testing. Because we don't control the operating environment, we need to make sure that what we ship is as good as it can possibly be, because the cost of patching is so high. So we're really trying to find the biggest bang for the smallest buck as we move around. And most of that comes from finding things to do where we don't just get the primary benefit from that activity, we also get a whole lot of secondary benefits from it as well. Otherwise, it's just not valuable enough for us to spend any time on. But because we are also sales and support, those concerns naturally feed into our development life cycle. We don't need to have like error budgets and things that create bridges between operations and development, because anything that we do that makes supporting the software harder, we also have to pay down at some point because we're the support team. So that's a little bit about us. I'd like to now cover some fundamentals that's going to frame the ways that we test our software. So if you're in here, you probably already have some idea of why testing is important, but I thought I'd cover it anyway. Over time, our reliance on software is always increasing. The places where we depend on software is always increasing. The complexity of the software that we rely on is also always increasing. And so as a result, our exposure to and the impact of accidents as a result of software issues is also increasing. And so our engineering practices need to keep up with that change. Otherwise, we'll end up in a world where software never works, which is definitely not the one we have now. So I've worked with a bunch of really good testers over time, and they all share this one key property, which is that they're not trying to prove that the software they're testing works. They're really trying to prove that it doesn't. And so that shapes the way that they attack software, so that they're always looking for a flaw that they are sure is there. And when you go looking for them, you find them. So really good testers are like toddlers. If you give them your favorite mug, it's going to get smashed. They're not going to treat it delicately like you would. So testing is ineffective if it's ad hoc. If you just go and write some unit tests as you're developing your software, you're not effectively going to be proving that your software doesn't work. You're going to be influenced by whatever biases are present at the point that you're building it. So in order to be effective, testing needs to be in service of a goal. And so to define that goal, we're going to have a look at some of the methodology from safety engineering, which is a branch of engineering used in like truly safety critical industries. Most of our software, hopefully, is not safety critical. If it is, you're probably already aware of all this stuff anyway. But we find that the ideas from safety engineering are actually still useful even outside of that context. So they're used quite a lot in SRE methodology, is influenced by safety engineering a fair bit. And they're useful for us in development too. So from a safety engineering lens, the goal of testing is to identify hazards in our systems while we still have a chance to eliminate them. Where a hazard is a state of our system that, if you combine that with an unfavourable environment, it can lead to a loss. A loss is defined by the system stakeholders, and it also comes from expectations from the system's users, who are effectively stakeholders that we tend to ignore. So a loss could be a financial loss, it could be data loss, it could be some sort of exposure, anything of that sort. And so we define safety then as the freedom of conditions that can lead to a loss, and so the absence of hazardous states. Reliability is a term that we throw around quite a lot. In safety engineering, it has a specific definition as well. And so a reliable system is one that doesn't deviate from its design. It does what it's supposed to do the same way all the time. A safe system doesn't deviate into hazards. And so as software engineers, this can be difficult for us to accept, but increasing system reliability doesn't necessarily increase system safety. These are actually distinct properties. Reliability is a property of components of a system, and safety is an emergent property of the system itself. And you can't talk about safety without considering the environment in which the system is operating in. So a component is unreliable, or it fails, if it stops performing as it is designed. Here's another weird take for you. Software never fails. Software always does exactly what it is designed to do. The problem is that your design may be wrong, but what it means is that hazards from software are always design flaws. The hardware it's running on could fail, but the software does what you told it to do. The good thing about the fact that software never fails is that it means that all of these design flaws can be identified through testing, and we can fix them as the system is built. We don't have to wait until we have a system and then try and kick it and see if it falls apart. We can do that as we build it because it's pure design. So testing is for identifying hazards in our software, and hazards are design flaws that let our system enter undesirable states. Unfortunately, we can't just exhaustively list all of these states and the ways that we can enter them, because in most systems, that's too complicated. There's too many possible states. So if we want to identify hazards, we have to be strategic. And it all comes about because of complexity. So there's a definition of complexity from safety engineering that I really like. It defines complexity as a measure of intellectual manageability. That is, a simple system is easier to understand than a complex system. Anything that inhibits your ability to reason about what your system does increases its complexity. And that also means that complexity is subjective. Different people perceive the same things with different levels of complexity, and our definition of complexity changes over time. So a history of systems could really be thought of as in continuously inventing better processes and tools to augment our understanding so that we can develop and operate ever more complex systems over time. And to do that, we have two key tricks that we as programmers tend to pull out in all areas of our lives once we've gotten really good at them. The first is decomposition. That is, you take a big complex problem, you break it up into parts, you solve each of those parts individually, and then you stick it back together at the end, and hopefully you get something that looks kind of like what you started with. The second is abstraction, which is the opposite. You take a bunch of things that are possibly on fire, you find a sufficient simplified representation of them, and then you treat it as that thing. Those are our two tricks. The problem is that complex systems don't tend to neatly decompose or abstract very well. You can't find sufficiently small pieces to treat them as, and then put them back together and get the same result. And you can't wrap all of that complex behavior together and treat it as something simpler, because the behavior of these systems emerges from the interactions of those components. So you have to consider the system more holistically in order to effectively test it. Okay, so now let's look at some application. So we'll start with the humble unit test. So when we're developing a feature, we may write a bunch of tests a long way to help us understand what we're building, or to, in my case, I tend to write a lot of unit tests as like a to-do list. So I'll be working on something and think of a case that it needs to handle, or some property that's important, write a test for it, leave it unimplemented, and then come back and fill them all in as I go. So these kinds of tests, they help us early on, but they're not super useful over time because they tend to be really tightly targeted at some specific thing that we happen to think about at the time. And so we tend to couple those tests very tightly to the code that they're testing. So as an example, I will show you, so here's a function that compares two strings with case-insensitive equality to tell whether they're the same. So two strings that have is that green readable there, by the way? Yep. Yep. So the implementation is not super important. What's important are the tests. So we write this code, we're going to compare two strings for equality, and here's the sort of thing you might expect to see as you're going around. You think of some cases of some strings. We want to know that strings with different casing compare the same way, and Unicode is kind of important. So we better make sure we've got a case that tests the case folding for Unicode. And that's all very nice and simple. Our tests pass. So normally what I will immediately do with this kind of test is then rewrite it to look something more like this, which in XUnit these are like theories. In Go they call them like table-driven tests. You basically take all of those cases that were individually laid out, and then you create yourself a little table of inputs and expected outputs, and then you run the code once over all of those, which is better because now we have one dependent line of code in our test instead of 5. And when you look at it this way, you can see that there's some clear deficiencies in our coverage in these tests. We're not checking whether strings should not be equal. And we had this issue in our string equality for a while. So we had string equality, it was correct. I then came along at some point and refactored it for some like clippy lints and made it not correct. The tests didn't catch it. We didn't catch it, and it lasted for about 5 years before we actually noticed that we weren't correctly comparing strings. So what was the problem? The problem was that our approach originally to testing those was just based on whatever we thought about at the time. There wasn't any rigor in our attempt to break our string equality through our testing. So what we can do instead is treat our tests as a bit more of like a workbench. So they're little scripts that have access to all of the internals of your system that you can spin up and you can run to test hypotheses. And the end result that you get is a more permanent artifact. So we do some hazard analysis and we write some tests based on those hazards that we identify, and we then expand our focus. Instead of just looking pigeonholed at the thing that we're currently working on, we also look at the surrounding context. So to give you an example of that, if we go back to our string equality tests, after we fixed that bug in the string equality, I then went and revisited the testing on that and decided to have a bigger look at what we were doing. And so we then built up a set of cases around the relationship between like equality and contains and indexing and regex, having a better look at Unicode case folding. So any Germans in the audience will recognize this little fella, the sharp S, which in some versions of Unicode will fold to two S's. So not only does it not fold to the same character, it folds to more than one of them. That's less of an issue in recent versions. It now folds to the uppercase sharp S. Another one is these two characters for complex numbers. These are characters that are considered equal but don't fold to the same character in older versions of Unicode. So thankfully, complex numbers don't exist, so nobody uses those characters. So what that ends up looking like is this case here. So this is what we ended up coming up with when we revisited those tests with a more antagonistic mindset. So we produced effectively like a spec for what string equality means, which is if two strings compare as equal, then any case folding of those two strings should also compare as equal. So case folding and the case conversion from upper and lower case should be equivalent. They weren't in older code that we were using. If strings are equal, then they should not be not equal. If they're equal, then the index of should be 0, and contain should be true, and then a case-insensitive regex, because we also support regexes, should also be true. So they should case fold in the same way. And how that ended up coming out is that we have a similar set of cases in a table, but we rely much more heavily on being able to permute those input cases in order to get much more effective test coverage without having to think of all the possible combinations of string, like substring equality and length. So we still have a fairly low amount of dependent code in here, but the shape of the test is covering a whole lot more ground than it was before. And this sort of thing is really hard to write when you're first building out a feature. It's difficult to get into that more holistic mindset when you're sort of rat-holed on whatever the exact problem in front of you is. So we have to revisit our code if we want to be able to test it effectively. So there was a bit of a hint in that last sample about what we can do to make fewer tests work much harder. So normally we're thinking in terms of concrete outcomes. Given this input, when this happens, I expect this output. And so we come up with a bunch of those. So now we're going to start looking at, instead of thinking about concrete outcomes, we're going to be thinking about properties. So that is, for all inputs, we expect some property to hold. So to give you an example of that, let's have a little look at, I've got a little function here. It doesn't do very much. I've basically just stripped all the functionality out of it and left some branches. And so we have our little table that we had before with one of our inputs. And so if I run that, what gets output from here, can everyone see that all right? So this is a coverage map of the function. And so we can see that we've hit one branch. There are 3 more that we haven't been able to reach. So we would have a look at this function and see what it takes to reach those branches. So we've hit the bottom one. So let's have a look at this branch. So we've got 3 inputs. A needs to be greater than B, and B needs to be greater than C. So we could have 2, 1, 0. So let's try that. Okay, so we've successfully hit another branch. So now let's think about another one. We haven't hit this one. So if A is greater than B, but B is not greater than C. So if A is greater than B, but B is not greater than C. Okay, we've managed to hit another one. So now we've got one more left to do. So that is if A is not greater than B, but it is greater than C. So that could look like this, I think. All right, there we go. We've just achieved 100% coverage on this function with 4 branches. But there's a better way to do that. And so what we can do is, instead of having to list all of these cases out, what if we just pick a bunch of numbers at random and then we run those? So I'm going to ignore this one so it doesn't influence my coverage. So that's pretty good. That looks like it hit all the branches. It would probably take me quite a lot of runs to run this without it hitting one of them. But for anything more complex, I'm unlikely to achieve very deep coverage just by picking random inputs. We can do slightly better than that. Most things that fail are going to fail at the edges. So what we're going to do now, I'll just ignore this one. So what we're going to do now is roughly the same thing, but we are going to use a function to give us an integer that is either going to be random or some interesting integer, which in our case is going to be the smallest value, 0 is kind of interesting, or the largest one. We're going to try and find some overflows. So that manages to do everything as well. But if we had some conditions doing arithmetic, then we'd be more likely to find accidental wrapping and things like that using these interesting integers. And so that then leads fairly nicely into property testing frameworks. So a property testing framework like Quick Check in Rust will basically do this for you. And so instead of you having to come up with a set of interesting cases yourself, it pre-bakes a bunch of interesting ones for you, and it will then also reduce any failures down to the smallest value it can find that fails, so that you can then plug that test case back into this sort of a test that you will also have alongside and get some repros for past failures. So there are lots of places where we use this pattern in Seek. So as an example, I talked about the query optimizer earlier. So the query optimizer has to maintain the invariant that the query that you're going to run is semantically equivalent to the one that it was optimizing before that, which is actually really tricky to do, especially when optimizations build on each other in order to further transform the query. So we have a little bit of infrastructure that will fuzz the query optimizer. So it generates some random queries. It does some basic constraint solving. So when it sees something like x is greater than 5, it knows x is numeric and it has to be greater than 5 in order to exercise the query. We then produce a sample data set that satisfies those constraints. We then run the query with permutations of optimizations, and we make sure that the resulting query is semantically equivalent. And so that looks a little bit like this, for instance. These are, so an example of a query plan. We have a lot of cases like this, for instance. I forgot to mention this one, where instead of having to list cases out manually, we have expected queries and plans, and we have a boatload of those cases. So when we come up with new ones we need to add, they just go into the case folder and we don't have to write any code to add more cases. So to build on top of that, we then have this query fuzzer, which does all of this. So when it finishes, so it does things like, for instance, it's generated a query here where we're getting a count of one property and then selecting two others. So P2 is text and W0 has to be has to be a Boolean. We're then grouping by them, and then we're then ordering by a bunch of random things. So this helps us find weird edge cases in the way that we may evaluate or optimize different operations. And so the row set that it came up with from that has then got values for all of those predicates that appeared in the query. And when those fail, we can then add the repro similarly to the text file we saw earlier, and we'll continue to check that repro. So another example, we have a column store that we've been building. Column stores are super complicated because they are just bags of optimizations. So basically everything is a specialization. So as an example, if we're reading out some columnar data, we have some integers encoded in a particular encoding. This is run length encoding. We then also have a bit mask that tells us which of those, which rows have values for those integers. We then also have a row mask, which is the query, which we intersect in order to read some certain values from the RLE, which means decoding it in a particularly efficient way. And so that's complicated in itself, but on top of that we have other encodings. So we may split values for columns into multiple different masks and then need to handle those differently. We may have columns encoded as dictionaries with indexes. We may have columns writing deltas where we can't sparse read them. All of these things come together to produce a set of ways to read a column. We then multiply that by all of the operations you can do on those columns to like aggregate them or distinct them or select them. And then we have a massive matrix of things that we need to test. So to make that a little bit easier, what we have built is a test harness that produces every possible encoding of column, and then for each of those runs some kind of a query over some sort of access pattern. So in this case, for instance, we have, what have we got here? 3,000 rows with 3,000 unique values. They're timestamps. So we're then going to read all of the rows from that. And no rows requested, I can't remember what that means. And we've got some alternating reads. Basically every possible way that we can read is covered by that. And so that lets us then build cases for aggregation, reading, distincting, everything on top of that, and we get all of the different combinations basically for free. Okay, so now we're going to look at instrumented fuzzing. So far we've basically been throwing random inputs, more or less random inputs at our functions in order to exercise as much behavior in them as possible. So now we're going to look at how we can use coverage information directly in order to figure out better inputs to give to our functions. So the way that a fuzzer works is we have a queue of inputs that we're going to test. We pull an input from the queue and we mutate it in some way, we change it. We then run the target function and we trace the execution path. We then try and reduce the input that we got until the path that we execute changes. And then we push that reduced input onto the queue. Every time we see a new path, we add that input to our corpus, and so then we build up a set of interesting cases. So I'll show you how that looks. So to introduce fuzzing, we're going to build the world's crummiest fuzzer. So here's our test function from before. So I run that, and we have our coverage map that we had before. The first thing that I'm going to do is add a module that is going to be our fuzzer. And so what we want to do is on each branch in this function, we want to note that we've hit a branch. So I'm just going to drop those in there. So far it doesn't do anything. But what we're going to do is, what do I need? I'm just going to add a few of these so I don't have to come back and add them later. Panic. Okay, so what we're going to do is in each branch, we are going to assign a variable which denotes the current path that we're in. And so the way that we can do that in Rust is use, I have a little hashing utility, I'm just going to pull that in as well. So the way that we can do that in Rust is that its panic infrastructure lets us get the location of the calling code. And so with the track caller method here, we get the location of the caller, which is like the line number and the column and everything. It's sort of a unique identifier for the code that we're currently running. So what we're going to do is we're going to hash that. We're going to hash that location, and then we're going to add it to our path. So first, what we're going to do is we're going to increment our path so that it shifts, and then we are going to XOR the current hash into it. And so what that means is that if we hit the same branch, but from a different incoming point, then we get a different hash. So it's a hash of the path we've taken, not just of where we currently are. So the next thing that we need is a way to execute our target, which is just going to be a function. And we're going to return the hash at the end. So first, I'm just going to reset the path, just in case we panicked or something like that, which is kind of what you want fuzzing to do, is to find things that break. We're then going to execute our function, and we're going to return the path at the end. So far, so good. Just make sure it even builds. Does not, because I can't type. And now what are you complaining about? That's also a function. And where are we there? 44. Oh. There we go. Okay. So far we've got those. So the next piece of the puzzle is the actual fuzzing harness itself. So what we're going to do, there's a few inputs to this that I'll explain along the way. So we have a way to track coverage in a function that we execute. We're going to run our fuzzer for some number of iterations just so that it finishes. We're going to give it a set of input cases just as a starting point. We are going to give it a function to reduce an input into a set of presumably simpler or smaller inputs. We're also going to give it a similar function that will permute an input, which is to create some new set of different inputs from it. And the goal in the permutation is to try and exercise a different path. And then we have our target function itself. So that is the inputs to our fuzzer. So the first thing that we're going to do is we're going to create a corpus. The corpus is the set of unique mapping from the most reduced input to the path that it executes. We want to have one per path. And we're going to start with a queue. So for each of our iterations, we're going to do something, and then we're going to return the corpus at the end. Okay, so within each iteration, while we have a value in the queue, we're going to do something. And so then to repopulate our queue for the next run, we're going to run through what's in our corpus. We're going to permute it. And we're going to push that onto the queue. Cool. So for each input into the each entry in the queue, we are going to execute our target function. And then what we're going to do is we're going to see if we've seen that input before. Otherwise, we're going to add it. And then we're going to reduce it. And so if when we re-execute the function with the reduced input, if it's the same, then we're going to reassign. We're going to reassign it. So our corpus gets simpler over time. So we build it up and we reduce it to try and produce the most simple result that we can. So that hopefully will build, but it does not. So let me have a look at that. Okay, so what have I done? Well, I'm not returning something for a start, where I want that to output a vec of t, I believe. Yeah, that was my problem. Cool. Okay, so now we're ready to actually fuzz our target. So what we're going to do is we're going to call our function. And our input, we only have one input type, so we're just going to make it an array. We're going to do this 100,000 times. And now we have to provide our reducer. So what we're going to do when we reduce in this particular function is we're just going to halve each of the inputs. So the first, the second, and the third. Nice and simple. Then we need to permute, which is we're going to do this slightly differently. So for each argument, we are going to take that argument and we're going to produce a permutation that changes just that argument to a random value. And return that. Collect it into a vec. And then finally, we have the function that we are testing itself, which is our target, which then just unpacks the array and calls it. So at the end of that, I'm just going to print out what we got. Fix all the build errors. Which is because, where are we? Well, it's private for a start, that doesn't help. And the next complaint is that I am probably returning this is proving to be a bit of a nuisance for me now, isn't it? All right, what am I doing? So, here's the experience of working in Rust. Expected that it's returning a unit because, why are you returning a unit? That seems a little bit odd. That is what I thought it would be, but I've probably missed something somewhere. And so, what I will what's that? Yeah, so we're doing the reduction first, but I have somehow managed to, oh, I know what it is. I forgot to put in the input cases. There we go. We got there. Everything is hard. Okay, so we've built ourselves a really crummy fuzzer. It's exercising the entire function a bunch of times. And what it's produced out of this is a reduced corpus of cases that exercise each branch. So if I kept this running for a long time, then we would get some even simpler ones. But this is pretty simple. Like there's a -8 in there. But it's managed to, in this simple case, reduce a fairly interesting and minimal set. Okay, so now we're going to have a look at AFL. Not the one with the short shorts, not the one with the fuzzy bunnies either, the instrumented fuzzer one. So if you've never done fuzzing with something like AFL before, the experience is a bit like what rabbits will do to your lawn, which is they just demolish it. So AFL is a lot like the fuzzer that we just built, except it's more sophisticated in basically every way. And so it's not just good at testing our functions that have 4 branches in it, it tests extremely complicated software. So we use fuzz testing, and to demonstrate it for you, I had an LLM write me a spec-compliant JSON parser. So this is what it put out. I haven't even looked at it, it's pure vibes. But it got some tests, a fairly fat stack of tests, 28 of them. So it must be pretty good. So the way that we do fuzzing with AFL and Rust is there is a library called cargo fuzz, which makes life really easy. So you write a binary as your harness that AFL is going to run. When AFL is available, then we fuzz, we run the test. And when it's not, it needs to be. I do it with a cargo feature just because AFL hooks into your build step, so it ruins your normal build if you are not building with AFL available. So what our test is going to do is very simple. We have a spec compliant, apparently, JSON parser. So we're going to compare it with a known good, a model. And all I'm going to do in this test is just make sure that if one parses successfully, then the other should as well. So we can run that. And so what AFL does is it's immediately finding crashes. So there are actually some problems. So while AFL runs, I'll show you the sort of thing that it does. Forgive the tiny little screen here. I'll pull up some cases. So AFL has a queue, just like what we were looking at earlier. And if I look at some of the inputs, that's not JSON. That's definitely not JSON. Nope. It does this sort of nonsense, where it hallucinates pure garbage and then throws it at your function as many times a second as it possibly can, and it finds lots of bugs. So now that we have some crashes, usually if you start fuzzing something for the first time, it will immediately start crashing like this one did. So what I then do is I have, for all of my fuzzers, I have a test that checks that it passes for all of the inputs, just as a sanity check. And I have a test that reproduces all of the crashes. So AFL saves all of its crashes into a directory. And so we can, I then reproduce those and have a look at what happened. So let's have a look at some of these. In this case, which is, where is that? ID 7. So up in ID 7. So this big number, for some reason it treated it as an array. That doesn't seem correct. I might be looking at the wrong one. This one, it seems to have parsed garbage and so forth. So what I will then do is then feed those back in, fix up all of the crashes. Once the repros stop crashing, start fuzzing again. And then it will probably inevitably immediately find a bunch more crashes for me to fix. And so we keep doing that until it no longer crashes. If you're wondering how long you should fuzz for, so over in, let me increase the size of that a little bit. Normally when you run AFL, you get like a little TUI like this. Up in the top, there's cycles done. So if you remember in our toy fuzzer, each time we emptied our queue, we refilled it. That's a cycle. So what AFL does is it colors the cycles done field so that while it's still finding interesting paths in your application, it'll stay magenta. When it kind of stops, it'll go yellow. And when it hasn't found any new paths for a really long time, then it goes green. And that's usually when you can be pretty confident that you've exercised your whole program. How long that takes depends on the software. Sometimes it takes a day, sometimes a couple of days, sometimes a couple of weeks. You could be running it like constant fuzzing effectively and always finding things. So that leads me to a point about coverage. We've been looking a lot at coverage and how we can, with less input of our own, improve the coverage of our testing. But coverage doesn't necessarily tell you what you think it does. If you have code that does not have any coverage, that tells you something. Nothing is testing it. But if you have code that does have coverage, that doesn't necessarily mean that it's correct. What it's actually telling you is that you have coverage over some property. And your choice of property is still really important. So as an example, we fuzz test our JSON parser. We made a change a couple of years ago where we allowed some more sparse parsing out of that. And so I refuzzed it, but I didn't fuzz that change specifically, and it turned out to be wrong. So there's a lot of the bugs in fuzzed versus unfuzzed kind of divide. And yeah, you need to also think about what fuzzing actually tells you. So now let's talk about models. So a model is where you compare your actual real McCoy system against the fake McCoy, the simplest possible model that demonstrates its behavior and is so simple that it couldn't possibly be wrong. So they're useful for like specialized data structures where they tend to behave like a B tree or like a queue or like a set. There are robust, well understood implementations of those things that you can compare your data structure's behavior against. So our on-disk key value store, for instance, is a map, except it is also on disk. And so we can compare it against various operations on it against what we do with an in-memory map and then make sure that we get the same result. They're also good for simulating things, so simulating I/O failures, memory safety. So in Rust, there is a tool called Miri, which is like a memory tester. So it simulates a memory model and runs your code against it, and it catches violations for memory safety. So we use it for fault injection as well. So error pars tend to be pretty dubious because they're hard to exercise normally. So you will often find, if you haven't been testing them, that code will fail. There's a whole lot of stuff that is supposed to happen, but it's never been tested and it doesn't work. So as an example, we're going to have a look at some fault injection. So I have found over time that I/O is extremely reliable and it never fails, except in environments where it always does. So we have a file system abstraction layer in our storage engine, and we use that to inject faults in various tests and make sure that we handle those gracefully. And as a nice little side effect, the fact that we abstract from the file system means we can actually also run our database engine in WASM, which is kind of cool. We don't use it for anything, but it's good to have. So as an example, I have a test here, which is opening a file and reading from it. And so what I want to do, I think that oh no, it has, okay. So I'm going to introduce, wherever it is, I can't read it in this theme. This is not my usual theme. I'm going to introduce some faults into this. So I'm just going to restore some code because I learned from my last attempt at trying to live code. So what we've got is a thread local that stores a set of faults that we may want to hit. The faults may be we failed to create a file, or we failed to read, or we failed to write. And we then have a function that at various points we can check whether a fault should occur. And we have a way from the outside to inject a fault into the process. So it's slightly intrusive in the code itself, but the idea being that because we've abstracted this away, that's kind of its thing to do. So it's not something that bleeds outside of this module too much. So we're checking some faults now. And what I want to do in my test is I want to make sure that when I read, if we get an interrupted error, then we just try again. So if I run that at the moment, it fails. Hopefully because it fails, it doesn't compile. Yep, it failed because we got an interrupted error. So what I then go through is have a look at my read code, and there is a case missing in here, which is that if our read fails with an interrupted error, then we should do something about it. And now when I rerun my test, it passes, and we're successfully checking that we handle those errors correctly. So something to be careful of when it comes to models is tautologies. So if you're not familiar, a tautological statement is a tautology. So it's a statement that tells you nothing. No information enters or escapes its little universe. They're useful in logic, they're not useful in testing. So as an example, you end up in this state when you have tests that replace everything with mocks and models, and so you end up not actually testing any real code. I ran into this issue actually fairly recently in our CLI. We have like a forwarder process that buffers data on disk if the seek server is unavailable. I had a file system abstraction very similar to the one that I was just showing you that we used in our tests to simulate various kinds of failures, but we only tested against the mock file system, not the real one. And there was a case it didn't handle, which was on Windows, you often can't delete a file if somebody else has it open somewhere. Linux doesn't care, but Windows does. And it didn't cover that case, and that failed in the field. So you have to be careful of making sure that you're still testing the real system and not just poking at mocks. So I want to quickly talk about simulation. So is another way to use models more at design time. So this here is a graph. I've just converted it into black and white. It shows storage. So the darker areas are recently buffered data that are expensive to read, and the grey areas are nice coalesced sorted data that's cheap to read. We don't want to rewrite data lots of times, so we buffer it at the front and then we compact or coalesce it into the immutable files over time. We don't want to have to rewrite that. There's something going wrong in this process though, because we have these stripes of buffered data. We don't want those stripes of buffered data because those have to age out over a much longer period of time. So what we have built for that is a little simulator that I'm just going to zoom out a little bit while this goes. So what it does is it runs our coalescing algorithm over a bunch of simulated rates of ingestion and volumes of ingestion and spread of ingestion, which is what affects the shape of the files that then informs coalescing. And it makes sure that we don't end up with those little gappy regions, regardless of the spread of data coming in. So we recently added that, and we also use it on our newer feature that we've been building in the column store to, from the get-go, have a better idea of how the underlying files will get organized based on different rates of ingestion, so that we're not guessing in the field when customers tell us that their queries are slow. You've got to be careful when it comes to simulations of biases, again with models, which is that simulations encode our bias of how we think things should work, not necessarily how they actually work. And the same is true of our choice of properties to test. You have to pick the right thing. So we always need to bring the focus back to the goal, which is to identify hazards. One of our most useful techniques that we use for testing seek is dog fooding. So we use seek ourselves constantly, and a lot of our bugs are actually found through dog fooding. So we live in the mess that we create for ourselves. And that's where most of our really weird bugs get caught. We also do burn-in testing and nightly benchmarks and things that help exercise the software more realistically. I want to try and finish a little bit on talking about the kind of testing that you do when your users have already done it for you and broken stuff. We focus a lot on root cause analysis when we are looking at failures. What broke? What was the thing that went wrong? Usually we'll try and blame the user if we can, but sometimes we can't. But most of the interesting investigation and our opportunities to improve start where root cause analysis stops, which is it's best to focus less on the root cause, the thing that broke, and more on contributing factors. So to give you an example, I talked about the string equality bug earlier, where we managed to introduce a bug in string equality that went for 5 years. If we stop looking at the code that broke, there's a bit of a pattern that emerges, which is the tests were deficient. Why were the tests deficient? They were introduced in a big PR with like 12 other methods that also had a handful of tests. Why didn't we catch the regression in the PR that introduced it? Well, it was also really big and it changed a whole lot of unrelated code. So a common theme between those is that bugs appear in big PRs, so we should stop writing really big PRs. But that kind of analysis is missed if all we do is fix the bug and move on. So some takeaways for you of where you can start. Stuff that's not already tested won't get tested later. If you find a bug and there's no easy way to write a test for it, it will not get written. So try and make tests easy to add so that they actually will get added in those sort of drive-by regression scenarios. Look for some common themes in recent bug reports in areas where you may have testing deficiencies, and they may not even be in software at all. Maybe most of your bugs come from misconfigurations in deployments, and try and think of ways that you can catch those better. So to wrap everything up, effective testing has a goal. It's to identify hazards in your systems. You need to keep that in mind as you're testing so that you're constantly trying to find flaws and fix them. Don't try to prove that your software works. Try to prove that it doesn't, because you know that it doesn't. Layer your approaches so that you can improve your overall safety nets. So lots of unit tests, lots of integration tests, fuzz tests, simulations, testing in the field. All of those things come together to help. And try and get creative. Don't just stick to what you may have seen before. Try and think specifically about your scenarios and your needs and what you can do to improve your overall software quality. And so I've got a couple of resources there just to finish up. The first is a safety engineering textbook. So Nancy Leveson is sort of the canonical researcher in the safety engineering space. She has a bunch of books, Safeware and Engineering a Safer World. This one is an introduction to safety engineering. It's a great overall look at safety engineering. The second is the Entropic Thoughts blog, which is where the idea that software never fails comes from. They also have a bunch of like analysis of things like the AWS outage last year from a safety engineering lens, which are all very sort of prescient and software oriented and interesting for us to explore. And finally, a link to AFL if you want to fuzz your own code. You can fuzz .NET through AFL as well. It's not all just Rust. Don't know if we've got any time for questions, but thank you very much. Are there any questions? Yep.
Do you use it so your query, that text view of your query planning, I don't know what you call that, but do you baseline it? Like, do you check that in and then when it changes?
Yes. Yes.
Okay.
Yes, we do.
Yeah.
And we have a simple way to make bulk changes to them, because sometimes we'll like rename something or rework them in a way that trivially changes all of those cases, but it's just not interesting because it's not changing the semantics. But yeah, we check those in so that whenever we change behavior, we see query plans change as a result. Yep.
How do you tell if two query plans
So for us, it's a little tricky because of we don't imply ordering unless you put an order by in. So if you have a result set with 50 things in it, the order in which you see those 50 things is undefined unless you have an order by. So if you then have a limit, then the set of things you see altogether is undefined unless you have a limit. So what we do is we run the query with no limit so that we get the full set. And then we run the query with the limit and we assert that the things that we got are a subset of the full result set.
So mostly it's based on the results the same?
Yes, so we have a simpler job than like regular programming languages do in that our domain is quite constrained. So it's a general problem in compilers to prove the correctness of optimizations, but we can do that fairly simply just by asserting on the result that we get out of it. So you had a question?
Have you tried mutant testing? This argument with a lot of principles to show AFL was interesting to discover, but its edge cases are used as branch. But what about mutation testing?
I haven't actually really tried it too much except via LLMs. So there are frameworks that do it much better than an LLM will. It was just a fun way to play with them. But yeah, the idea there was to have it fudge up the implementation and then look for any changes that it can make to the implementation that don't break tests and then write a report of those, which I think is effectively what mutation testing is. But setting my GPU on fire to do it instead of doing it really easily. But yeah, we don't do a lot of that in Seek itself yet, but it would be interesting to introduce as well. Yep.
Which technique would be useful when it comes to identifying, let's say, issues with capacity, high capacity events, when, for example, a query starts to fail and you have lots of data on it?
Oh yes, where you get like the cascading kind of failure from that. I think simulations would probably be the best way to do that. So if you have a way to take the actual behavior of your system and then isolate the sort of the queuing behaviors between those and then simulate filling those up and how they behave when you have full queues, then that is what I would probably first reach for to try and test that. Any other questions? Nope. Awesome. Well, thank you all very much.